Hello and welcome back to another Physical Sciences 3 lecture. In the last time we started to look at some of the explanations of the physical properties of ionic compounds, and we saw that the melting point of these ionic compounds are dependent on the amount of electrons that are donated or exchanged. Okay, so we had potassium chloride and they exchange one electron because they've got 1 plus charge for potassium and 1 minus for the chloride ion, compared to 2 plus charge for the calcium ion and 2 minus charge for the sulfide ion. And so calcium sulfide will have a higher melting point because more electrons exchange, resulting in a stronger electrostatic attractive force. Okay, ionic compounds are hard and brittle. So we saw before that we have this lattice here, continuous lattice, and we have a nice structure of negative and positive ions, all arranged nicely. But if we distort this, so like let's say we push the top layer across, we suddenly get negatives with negatives and positives with positives, and what they want to do is repel each other. Okay, so opposites attract, but likes repel. Okay, so opposites attract, likes repel, so that means that they will want to push off against each other and cause a snap or a break. And that's why we say they are brittle, because they will snap and break if the structure is disrupted. Ionic compounds do not conduct electricity in the solid state. Okay, that's because there are no free electrons, as all electrons are localized, fixed with the ions. The ions are strongly held with the lattice and cannot carry charge because no movement of ions. So all these ions are held firmly in place, so they cannot move. They do not conduct electricity. Ionic compounds do conduct electricity when in aqueous solution or in the molten state when they have been melted. Okay, so when they are aqueous, they have been dissolved. Okay, dissolved, aqueous solution. They have been dissolved, and so it's like broken apart, dissolved, or being broken apart and destroyed. The ions separate from each other and are now able to move randomly. We say the ions now possess mobility, so able to move. When an electrical potential is applied, positive ions move towards the negative electrode, and negative ions move towards the positive electrode. Remember, opposites attract. So this movement of both types of ion is in opposite directions is a net movement of electrical charge and is called an electric current. Okay, so this one clearly is the positive and this one is the negative because we have our negative ions moving this way and positive ions moving this way. Good. And remember that electricity is just a movement of charged particles. So in the following table, identify which species would be electrical conductors and indicate the particles that carry the electrical charge if they do conduct electricity. Okay, so we can now want to look at these little brackets here. This will be the first time a lot of you have seen them. So this means that copper sulfate here is an aqueous solution. So so those Cu ions and SO4 ions will break up. We'll go into our Cu2 plus and SO4 2 minus. So we have those ions there. This one here is silver. So silver, yes, it will conduct and it will pass on electrons. KBr, and see how this is S here, that means solid. So we've seen that AQ is aqueous, S means solid, and we also have little L, and that's liquid. Okay, so if we have KBr here in a solid, they will not conduct because they are there is no free particles moved. There is none to charge. This will not either. So this is a liquid, which means that our NaI particles are all in the are all together in a lattice, similar to if you have water, we have a bunch of water particles. They are just all moving around, well, they're all just there, and they are, we would call that H2O liquid. So that's H2L. This is different than if it was, let's say we had, you probably wouldn't see this, but H2O aqueous would be a bunch of H pluses and O2 minuses going around in the solution instead. Okay, so then they would be able to move, and they would have that would be charged particles. But that's the difference between a liquid and an aqueous. In aqueous, the actual solution is dissolved. So these ones would be charged particles dissolved in the solution. Okay, we haven't spoken about that too much, so hopefully that's sort of clear. A liquefied zinc is still able to conduct electricity because there'll be free electrons. And there is no way that an NaOH solid could move because there are no free moving of particles. Okay, explain in terms of bonding models why copper metal is a better electrical conductor than a solution of copper sulfate. Okay, why is copper metal is a better conductor, electrical conductor than a solution of copper sulfate? Okay, so a copper metal conducts electricity due to electrons, due to free electrons, delocalized electrons, which move easily throughout the structure or lattice. Copper sulfate in solution conducts electricity by the movement of the ions. Which are larger and likely to collide. Okay. I'll explain that in a minute. Collide with other moving ions as well. Okay, so if we look up here, if we have these particles here, we have some moving this way, some positive ions moving one way, and some negative ions moving the other way. And as they move, they'll actually bump into each other, so they can't move as quickly as tiny electrons. Okay, so that's the reason why why it's slower to conduct electricity. It seems quite simple, but that is why. Explain in terms of ionic bonding model why solid sodium chloride does not conduct electricity, but an aqueous solution does. Okay, and this is simply because I'm going to write down as this NaCl solid has bound particles by electrostatic forces. In solution, NaCl aqueous, the ions have broken apart. Sorry about my handwriting. Broken apart, and are free to carry charge. Alrighty, And we'll leave it there. We've got covalent bonding up next.